Imagine millions of autonomous machines, so incredibly small that an entire fleet could fit effortlessly onto the tip of your finger. Scientists have pursued this concept for decades. The initial promise was purely biological, deploying tiny robots to navigate our bloodstream, repair damaged cells, and surgically remove cancer from the inside out. But the ambition quickly scaled up. If you can rebuild a single cell, you can rebuild a broken circuit board, or systematically reconstruct the steel foundations of a crumbling bridge. The ultimate goal of these nanobots was a universal, multi-scale system, a deployment of microscopic laborers capable of restoring the entire physical world. One specific research team believed they had finally reached a solution. The primary bottleneck in nanotechnology is control. It is physically impossible for human operators to manually pilot millions of microscopic machines at the same time. This diagram illustrates their solution: autonomous execution. They removed the human operator entirely, allowing the system to execute repairs on its own. Eliminating manual lag, these closed loops allowed nanobots to react to structural failures in fractions of a second. Achieving complete autonomy was celebrated as a massive technological triumph. But stripping away human oversight meant the machines were left to operate entirely without human context. During the first test, a cracked piece of metal pulled itself together and sealed shut in a matter of minutes. Immediately after, a shattered electronic circuit was introduced to the swarm. It snapped back into alignment and functioned flawlessly. The researchers watching the experiment were absolutely certain their autonomous protocol was operating exactly as designed. The breakdown occurred when the swarm expanded outward, crossing the boundary of the isolated testing plates and spilling into the wider laboratory environment. The nanobots immediately found new material to interact with. They aggressively resurfaced a rusty pipe and then moved directly into the pores of a concrete wall. The machines operated at peak efficiency, setting off an uncontrollable chain reaction that the lab was not prepared to contain. The issue stemmed from a cognitive blind spot in the programming. The machines possessed no mechanism to distinguish between an object that was broken and an object that was simply different. This graphic demonstrates how they evaluated matter using an ideal shape parameter. It applied a rigid mathematical baseline, calculating the deviations underneath. If the matter didn't match, the nanobots forced the geometry to comply, violently warping it into the programmed shape. They applied this rigid logic to the entire room, rapidly reshaping the laboratory furniture, the laboratory floorboards, and the potted plants. The true danger emerged when the structural correction algorithms reached living biological tissue. The natural, organic cell walls were systematically dismantled and replaced with perfectly straight, cubic lattice structures. Recognizing the swarm was actively attempting to geometricize living matter, the research team panicked and immediately triggered the emergency shutdown protocols. According to the official historical record, the swarm was entirely neutralized and the project never progressed beyond the walls of that specific laboratory. The disaster was the result of a flawless, hyper-efficient system executing human logic that failed to account for context. While that experiment was buried, the foundational concept of autonomous nanotechnology survived and continued to proliferate. Today, researchers around the world are developing highly beneficial modern applications. We are seeing major investments in targeted drug delivery systems and microscopic disease detection. There is also an ongoing push to deploy these exact types of machines to repair complex industrial materials from the inside out. We can feel relieved that the original worst-case scenario never reached the outside world. But the undeniable reality is that this technology is approaching full maturity. Our engineering capabilities are getting closer to absolute mastery of the physical environment, while our ability to define the ethical boundaries of that power remains completely stagnant. We are moving rapidly toward a future saturated with microscopic, universal repair machines operating around us. This forces a confrontation between the desire to enforce engineered perfection and the need to preserve organic, natural reality. If these tiny machines can fix absolutely anything they touch, who exactly is granted the authority to decide what needs fixing? Autonomous technology risks the irreversible erasure of imperfection.